But let's look at one where we have something on 2 ropes, because these are ones that give people a lot of problems. And again, my drawing is imperfect here. Theta 1, theta 2. We're just going to say that theta 1 and theta 2 are equal, regardless of my bad drawing. So if we've got an object hanging on 2 ropes at some angle theta, we have a force of gravity down on it. Which angles have to be resolved here? Gravity? Force of tension? Yes. So, and I'm going to make this a sort of dotted line. Within each of these forces of tension, and I should color code these to make it clearer. Whoops. We have a force of tension on the y. Jeez Louise, that's terrible. It doesn't. If there is no surface, that's a fantastic question. If there is no surface, there is no normal force. No surface, no normal force. Suspended in the air, no normal force. We're going to talk about another situation later where there's no normal force. Yeah, if there's no surface, there's no normal force. So force of tension on the y, force of tension on the x. And where we have force of tension, oops, I guess I made that 2. Now in this case, like I said, theta 1 and 2 are equal. So you don't have to, let me get just another color of some sort. But we also have force of tension 1, force of tension y1. Those are really hard to read, aren't they? Force of tension x1. Yeah, those are darn near impossible to read. I apologize. Force of tension 1, force of tension y, force of tension x. So your free body diagram doesn't have to include that resolution of vectors. Well, it probably should. I mean, a classical free body diagram shows just the forces. The force of tension in that is enough. Now, that said, I think you'd be a fool not to resolve those vectors in your diagram, because it's really just way too easy to get confused if you don't. So let's look at solving for force of tension here. So let's do a quick sum of forces on the x-axis, and let me get that back down to real spacing. Sum of forces x. This thing is not moving side to side, so it's 0, but that is equal to its mass times its acceleration. Sum of forces is always equal to mass times acceleration. So we can talk about net force on each axis. We can also talk about overall net force. Okay, name me, and this is, of course, equal to all the forces one direction, all the forces the other direction. Give me one force in the Cartesian negative direction. Force of tension x1. Okay. And the other one, of course, would be force of tension x2 in the opposite direction. So these are in opposite directions. Because we know that this is 0, we know they're equal and opposite. We could take this down to a solve. Well, we know this is 0, so we can get rid of that. So we know that ftx1 equals the negative of ftx2. We didn't write expressions yet, but this is our angle theta here. So force of tension on the x would be equal to force of tension what? Let me do it in red. It's next to the angle, cosine. Force of tension 1 cosine theta 1, and this, of course, then would be force of tension 2 cosine theta 2. And that's a little algebraic proof. There are a few exceptions, but in general, when we've got something hanging on cables, if it's not moving side to side, we don't have to think about the x-axis. The horrible mastiff problem is one where we do because the angles are uneven, and this provides us a way, because we have proportions between the forces, the x-axis provides us a way to solve for those angles. But in general, in these kind of problems, we don't often need the x-axis. Not a bad idea, though. Just sort of solve it and set it aside. You've got that tucked away if you need it. But the y-axis here is where the action's really happening. And we don't know if this thing is rising or falling. We haven't been told. So we know that whatever the sum of forces on the y-axis is, that's going to be equal to its mass times acceleration on that axis, and its mass acceleration period, because there is none on the x. This is going to be all the forces up plus all the forces down. So, MA equals, name me a force up. FTY? Just FTY? FTY 1. We got two cables here. They're both exerting an upward pull on this object. Name me another force up. 2, I heard. FTY 2. Do we have any other forces up? No. Force down is FG. And that's the only force we have down. So, let's get our expressions completed for FT. And sometimes I complete my expressions and set them aside. Okay. So FTY1 would be FT1 sine theta 1. FTY2 would be FT2 sine theta 2. So here what we have is that the mass times acceleration is equal to FT 1 times sine theta 1 plus FT2 sine theta 2 plus, what's FG equal to? Mass gravity. Mass gravity. So at this point, we're down to just a few variables. We're down to mass, acceleration, gravity, and force of tension. And force of tension is what we want to solve for. Now we've got one more trick up our sleeve. We know that theta 1 equals theta 2, and we also know because of that that FT1 equals FT2. Whoops. FT2. Equal angles, equal forces. Which means that what we're really saying here is 2 times FT1 sine theta 1. Okay. So at this point, do we have a clean way to algebraically solve for FT? Yeah, we can cleanly solve for force of tension. We can even do one better. We can do MA minus MG equals 2 FT sine theta. We can simplify this. So divide both sides by 2 sine theta. Get rid of these. We can actually factor out mass there. We have m divided by a minus g over 2 sine theta is equal to the force of tension. Being able to get it down to the simplest possible equation matters because you're going to end up substituting things. Okay? Questions, comments, concerns?